Okay, welcome everyone. So let's begin. Let me share my iPad. Okay. Okay, so I see a lot of congratulations. So thank you everyone. So let's begin. Okay. Okay, so today's lecture is going to be a bit general and so we will be discussing tips, let's just say practical tips for doing ML. Okay, so throughout this course, so we learned a lot about different types of machine learning algorithms. I think majority of the course focused on classification. So we looked at a lot of classification algorithms, and we have also seen linear regression and dimensionality reduction and so on, right? So we have seen variety of machine learning algorithms. Now, one of the important thing that we did not cover much in the course is how to make use of the algorithms that you have learned in the course and apply them in real world problems, right? Like most of our examples in the class were kind of well structured data sets, while in reality, so when you go start doing machine learning, like as a machine learning engineer in a company, right? So you will face a problem and you have to come up with a machine learning pipeline to solve this problem. Now, that is when you will realize that the textbook algorithms that you have learned are not directly applicable, and you might need to do a lot of things on the top of it to make it work. Okay, so today's lecture, even though we will not cover this exhaustively, we will try to cover as much as we can about how to do machine learning in a more practical setting. Okay, so first let's start with the idea of end-to-end pipeline. Okay, so again, this is a very general lecture. So if you have questions, feel free to put them in chat or raise your hand. Okay, so any machine learning problem would have the following pipeline. Okay, so it's all data dependent. So you have data which is coming in, right? Now, once you have the data for the problem that you want to address, now you have to clean the data and make it ready for the algorithm to be consumed, right? So to give you an example, let's say we have what kind of problem? Okay, so let's just take a very simple running example problem, right? So let's say I am interested in predicting whether it will rain tomorrow or not. It's a weather prediction problem, right? Now, there are a lot of historic information that we could condition our model on to decide whether it is going to rain tomorrow or not, right? So we would have a lot of readings from pressure, atmospheric pressure, or the fog, or visibility level, whether it rained yesterday or whether it rained in the last 1 week, right? So you could have hundreds of features or probably even thousands of features. Okay, now you collect this data. Let's say you collect this data. Weather prediction is actually one of the very well-defined machine learning problems, simply because we have been recording weather information for, I don't know, 50 plus years, right? So now you have lots and lots of data. Now this data could actually sometimes have discrete attributes, right? It could actually have missing values, right? So to give you an example, let's say one day in the weather station, atmospheric pressure, the meter to track atmospheric pressure, is not working. Okay, so now you have that entry missing just for that day. Now, how do you fill this value, right? So there is a missing value problem, there is a discrete attribute problem, there is also the problem of class imbalance. which means it's not going to rain every day, right? Like rain might be rare. So you would have no rain, no rain, no rain, like for like 10 days, and then there is 1 day of rain. So there is a class imbalance problem too. So you have a lot of such problems in the data, and normally you would do data pre-processing. Okay, so now this data pre-processing is going to take the data set and do whatever changes you want to do. For example, if you're using a neural network and you have a discrete attribute, probably you would convert it. Okay, well, this is a quiz. Um, so I'm using a neural network and I have a discrete attribute. So how would I feed in this discrete attribute to the neural network? So can we see some answers in chat to see how prepared you are for the enter? One hot encoding. Is there anything else that you can do? One hot encoding is fine. Is there anything else? Okay, frequency encoding. Okay. Yeah, you could do a lot of encoding techniques, which would basically take the discrete entity and put it into a number, right? Like, so, like take this categorical thing and put it into a number so that you can feed this into a neural network. So then there is a problem of missing values, for which you would do a lot of pre-processing, which involves computing a mean to replace this missing values, or sometimes designing a regressor which would try to predict this missing value and so on. So there's a lot of data pre-processing step involved, and I somehow like removed this from the entire course, in the sense like we did not discuss about data pre-processing at all, like while in real life it's probably like a very crucial step in the pipeline. Once you have a clean data, then you pass it to your ML model. Now in this case you are doing training. Okay, so this involves designing a machine learning model and training it, and probably doing hyperparameter tuning and a bunch of other things, right? Now, once you're happy with your model's performance, then finally you deploy. Let's just call it as testing. Okay. Now this is the basic machine learning pipeline. Okay. Now, a general tip for you to, like, let's say you start a project on coming up with a new machine learning model for the problem in hand. The general tip that I have is always use a simple model, okay, and complete the pipeline so that you get some basic results. Okay, so always start with the simplest model that you could think of, complete the pipeline end to end. Okay, now if you want to improve the model, you would just work on the model part. So the pipeline is already ready, and you will start improving your model and get better and better results. Okay, so then improve the model. Okay, a general strategy is to always have a working system from the beginning of the project. Okay, so there are many benefits in doing this, right? Like, so like if you don't have a working system, let's say you're working on a complex project, coming up with the complete pipeline requires 2 months. Okay, now if you don't have the end-to-end pipeline for 2 months and you're just working on bits and pieces, it is very difficult to test these bits and pieces, right? Like, so instead what you should do is to come up with a simplification for the entire pipeline, like which could be done in, like, let's say a day or two. Now you have the complete simplified pipeline. Now you enhance the functionalities in the pipeline one by one. Okay, so now this has two benefits. Like, one, you can actually continuously test your code. Two, it also helps you psychologically because you have a working system. Like, it's not like you don't know if your system is going to work or not after 2 months, right? So that is the general uh, tip for setting up the pipeline. Okay, so then let's just call this whole thing as tip one. Okay, now the second tip or trick, whatever you want to call it, is to overfit the model with a single mini batch. Okay, you might have a data set of 100,000 examples or 200,000 examples or a million examples. Okay, now don't attempt to start training the model with the entire data set. Okay, so you should always take with just one mini batch, let's say 100 examples, and you try to overfit. Okay, so if the model overfits the single mini batch, okay, so then it basically means that it's a good sign that the implementation is probably correct, and gradient computations are happening correctly. Okay, so most often if you see that your model is not getting a zero loss with just one mini batch, then it just means that the implementation is not right. Okay, so it means that either the implementation is not right or your gradient computation has issues. Like some of the common issues in gradient computation includes putting a plus sign instead of a minus or a minus sign instead of the plus, which makes the gradient descent diverge, right? So there could be several reasons why your model is not working. You can easily catch that your model is not working if you are just overfitting for a single mini batch. Okay, so you should see a zero loss. Like, so you are using only one mini batch and this is the number of updates. Okay, your model and say this is, if this is the loss, your model should go to zero loss. If it is not, okay, maybe I'll use a different color. So your model should go to zero loss. If it is not going to zero loss, like, then probably something is wrong, because your model should have more capacity than a single mini batch for sure, right? Like, so in which case it should overfit. Okay, so now in this case, like, you're actually using overfitting as a way to test the correctness of your model. Okay, so that is the second one. The third useful trick, it's a tip, is you should always focus on good hyperparameter tuning. Okay, even though we have seen a lot of new optimizers which kind of claims that you don't need to tune the learning rate, like they're automatically tuned, I would always suggest you to tune your learning rate. Learning rate is probably one of the most sensitive hyperparameters in machine learning. So you should always try a couple of learning rates before deciding one learning rate. Okay, and also it's actually a good idea to list all your hyperparameters in a single config file. Okay, so that you know what are the things that are moving in your algorithm and you can easily control them. Okay, and another important like suggestion here is you should spend some time with each hyperparameter by tuning it separately to get a feel of its effect in the learning process. Okay, so spend some time with each hyperparameter, okay, by tuning it separately to get a feel of its effect in the learning process. Well, remember that, like, so we are talking about projects which are 6 months or one year in timeline, right? Like, so when you do such a big machine learning project, it is extremely important that you know what each hyperparameter is responsible for. So in that case, like, I would suggest you to do some like low computation experiment. You don't need to run for 1,000 epochs, like, so just run like 10 epochs, but try different values for each hyperparameter by fixing all the other hyperparameters, so that you actually know that like you actually know like what is this hyperparameter doing. Okay, now this sounds like a tedious process. If you do this in like 3 or 4 projects, after a few times you will actually start developing an expertise in guessing the effects for each hyperparameter. Okay, so training your training your machine learning model is still an art. So it requires a lot of internal intuitions on like how different hyperparameters would work, and gaining that practical experience is really, really helpful. Okay. And also another advice in this topic is always do a proper hyperparameter search. Okay. Now hyperparameter searches are costly. We know that, right? Like, so if you have 5 hyperparameters and let's say each is a real number, there are too many values to try, right? Like, so doing hyperparameter search is always like time consuming and computation consuming, right? Like, so you have to plan it wisely, like don't waste compute. So there are few techniques that people use to hyperparameter tuning. So the most common one is grid search. Okay. So in the case of grid search, let's say I have 2 hyperparameters, h1, h2, and let's say this is the range. Now I would try different combinations of these hyperparameters. In this case, I took 3 possible values for h2, 4 possible values for h1, and I'm doing all the combinations of 4 plus 3. Okay, I will try all these values and find the best hyperparameter. Okay, now this grid search is very extensive, like computationally extensive. So a more smarter way of doing this is what is known as the random search. Okay, in the case of random search, you would take these 2 hyperparameters. Okay, you would randomly pick points. Okay, okay, now this looks like structure, but you randomly pick points and do hyperparameter search. Find the region. Let's say this region looks reasonable. If you think that this region looks reasonable, then you would go ahead and continue more extensive hyperparameter search in this region. So you would recursively try to spot the best region for hyperparameters. Okay, so this is the second way you could try. And the third way you could try is to use more efficient Bayesian optimization for hyperparameter search. Okay, so this is out of scope for this course, like, but I would encourage you to go look up on so how to do hyperparameter search using Bayesian optimization methods. Okay, so any questions so far? Okay, so is it possible to use a kind of genetic search for hyperparameters? Yes, you can do that, right? So, but remember that it's hyperparameter search is extremely costly. Well, if you have linear models, then maybe you could do hundreds or thousands of hyperparameter configurations. But for let's say you're training a neural network which takes 2 weeks to train, you might not want to do like a genetic search. Is it possible to find the best parameters? You mean best hyperparameters? Yeah, well, that's the point of the training stage of the pipeline, right? Like, so you try different hyperparameters and pick the best hyperparameter based on validation set. Any other questions? Okay, so then let's move to the fourth tip, which is always organize your experiments. Okay, so it is very, very important that you organize your experiments, especially in a machine learning project. Typically, in a software engineering project, like you are using GitHub to track the versioning, right? Like, and to track the changes in your software code, so in the piece of software that you're writing. But tracking or versioning machine learning models is even more complicated. Why? Because you keep changing the structure of the model that you are using. And as this evolves over time, you want to kind of track what changes you did to this model, so that you learn something from this and make it more useful, right? So in this case, like, there are many ways, there are many softwares to track your machine learning projects. Okay, so like one of my recent favorite tools is called WNB, which just I think which stands for weights and biases. Okay, I call it WANB. So WANB is primarily a visualization tool. We will talk about visualizations shortly. Okay, but it is also good for experiment management. Like, so you can actually record the hyperparameters that you have tried so far. You could record like the range of hyperparameters, and like, so what was the result of your experiments, and you could track your code. So there are a lot of functionalities in WANB, which is very useful to organize your experiments. So I would highly encourage you to go check WANB, try it by yourself, and like make sure that your code is well organized. Okay, so then the next tip is checkpoint your experiments. Okay, so now this is another really useful practical tip that you should always make sure that you have a proper checkpointing before you start your project. Okay, so we will talk about two things here. Like what do I mean by checkpointing, right? Like, so what is checkpointing? And we will also talk about why should I checkpoint, or why should you checkpoint? Okay, so first let's define what is checkpointing. Okay, so by checkpointing, so what do I mean by checkpointing? By checkpointing, I just mean that like you are saving the current state of the experiment. Okay, now this is a good quiz again. So what are all the information in the experiment that you think are very important that you should save them? Okay, so parameters, hyperparameters. By parameters, okay, so basically, I'm going to call the whole thing as state of the model. Okay, the state of the model includes parameter and hyperparameter. Okay, that is fine. Anything else? Well, everyone is saying parameters and hyperparameters. Are those the only two things that we think are the moving pieces of the experiment? Execution time, well, like that is just your tracking, right? So the data, if it changes, that's a good point, right? Like, so actually there's even more to that. So let's just call that a state of the data iterator. Okay, so this actually includes which mini batch you are currently using. Okay, now why do I need to save the state of the data iterator? Okay, so maybe I should have first answered why should you checkpoint. So the basic idea here is ML experiments take a lot of time. The experiment might take 2 days, 3 days, sometimes even weeks. Okay, so now the side effect is your job might get killed often. So you might be running your experiment in your home machine, but there might be a power cut or someone unplugged the machine, right? If you're using clusters, clusters might go down. Now, let's say I have an experiment which has which needs to be trained for like 2 weeks. After 13 days, my cluster went down. Okay, now do I need to redo the whole 13 days of training? Like if I had a proper state of where I left, then I could just start from there, right? So that is exactly why the state of the data iterator is important. Let us say I have 100,000 mini batches to go over, and I am in the 55th mini batch. 55 is just too small number. So let's say I'm in the 1,000th mini batch. Okay, I have already seen 1,000 mini batches. If I can keep track and say, oh, these are the 1,000 I have already seen, these are the rest of the data mini batches that I haven't seen, So if I save that information, then I could start exactly where I left. Okay. And another important piece of ML experiment is the optimizer itself, right? Like, so state of the optimizer. Okay. So this actually includes all the bookkeeping variables in the optimizer. Okay. So another exam prep quiz. Um, what are the things that you want to save in, let's say, SGD with momentum? So I have SGD with momentum as my optimizer. Now, what are the things in SGD with momentum that I would like to save? Learning rate, yeah, that's good. What else? What else? Is that the only thing that we are tracking in momentum, like SGD with momentum? Yeah, so the momentum term itself, right? Like, so if you remember, there is a MT, like the momentum term. So you will be saving this momentum. So you don't want to lose that momentum just because the experiment got killed. So you want to keep momentum as well. Similarly, like if you're looking at something like RMS prop, then like you would be saving the denominator of your learning rate, like the RMS value, right? So each optimizer has some bookkeeping variables and you need to store them. Okay. So then you have training statistics. So normally you would have things like training loss, and validation loss, and a bunch of other things that you want to track. So you'll be tracking a lot of things in your experiment, and you just save those things as well. Okay, and and at last but not the least is the state of my random number generator. Okay, now this brings us to the another reason why should you checkpoint. Okay, so the first reason was MI experiments take a lot of time, so jobs might get killed. Okay, the second reason is actually to have a perfectly reproducible code. Okay, so that is exactly what we are going to talk about in the next section. But for now, like when I say I want a code which is perfectly reproducible, like I run this experiment again. Let's say the first time I run the experiment, I get 94% accuracy. I run this experiment again, I should get the same 94% accuracy. Okay, how can I guarantee that I will get the same performance? So I think someone rightly pointed out that in the chat that the initialization of the network matters, right? Like, so like the random initialization that you're doing, if it is going to be different in the second run, the performance might be different. So you want to save the state of the random number generator as well, so that your code is completely reproducible. Okay, now this is the second. Okay, these are all the things that you would like to track. There is also a third reason, like which I think is kind of covered in the first point, which is like if you want to run your experiments in clusters, even clusters have wall time. You cannot run your experiment for more than 12 hours, but let's say your experiment is taking 4 days. Now you have to restart your experiment for every 12 hours, and that requires checkpointing as well. Okay, so any questions about checkpointing? Any questions about checkpointing? Okay, so then we can move to the next point, which is reproducibility. Okay, now, can someone tell me why is reproducibility in experiments important? Maybe hand raise, and if you want to talk, or you could put it in the chat. Why is reproducibility important? For peer reviewing, that's a good thing. Okay. Share to compare with others. Okay. Any other reasons? Keeping track of experiments. Fine. Reusability. That's fine. Yeah. Random. I think I guess what you mean by random elements is like to control the randomness. Yeah, publishing. Yeah, so that's covered in peer review. Okay, so there are many reasons why you should have reproducible code, right? Most importantly, it is a requirement to do good science. So often we build upon someone else's work, right? So now it is much easier to build upon, like if the work is exactly reproducible and like you can work on the top of it. Also, like the fact that the work is reproducible means that it is not like by chance number that you got, right? Like so, and definitely it helps in peer reviewing because like if I have to validate your idea, I should be able to reproduce your performance. Okay, so we need reproducibility to do good science or better science. Okay, and to verify that someone else's hypothesis is correct. Okay, then also to build upon another person's work. Okay, but reproducibility is hard. So why is reproducibility so hard in machine learning? It's hard mainly because there are several sources of randomness. Okay, another general quiz. So now can you guys think about what are the different sources of randomness in a machine learning experiment? What do you mean by batches? Initialization is definitely one thing, right? Like so initialization. Okay, so yeah, so if you have something like dropout, so okay, so which means the model itself might have some probabilistic components. Okay, an example is dropout. We haven't seen dropout in the course, so if you don't know, it's fine. Um, the data split, or in other words, the data iterator might be different times. Like if the data iterator is going to give different batches, that is problematic, right? Like so, what else? Also, the randomness in deciding the mini batch or any sampling process. The randomness in sampling process. Okay, now there are many sources for randomness. Okay, so now how to make reproducibility easy? The general answer here is to control all the sources of randomness and always checkpoint your random number, a random state when you're checkpointing. Okay, now this is a tedious process. Controlling all the sources of randomness might be very painful, but remember that you're just doing this once in the beginning of your project, and once you have a perfectly reproducible pipeline, then you can very easily make sure that you're consistent in reproducibility throughout the project. Okay. Okay, so now that is about reproducible. Well, like another point to know here is there has been a lot of awareness in the machine learning community about reproducibility, and there are machine learning reproducibility challenges. In conferences, like which encourages people to go try to reproduce like a published paper in machine learning. Okay, I would also encourage you to go look at these ML reproducibility challenges. Okay, so let's move to the next. tip, which is how to report your models. Okay, so now where do you report your model? Let's say you come up with a new model, you're writing a paper, in which case like you will be explaining the model. Now, in the case of the Kaggle competition that you're doing, like you're writing a report where you need to mention what is your model and like this, like, and more, give more details, right? Like, there are many places where you will be reporting your model. Okay, now for better reproducibility, you should try to report your model in a detailed way. You should always list all the hyperparameters of the model. Okay, and you should always explain your hyperparameter tuning process, which includes telling the range of hyperparameters. Okay, and also always mention the best hyperparameter configuration you ended up using finally. Okay, and write a detailed, precise mathematical description of your model. So try to write precise description of the model. Your description should be precise enough that someone who wants to reproduce your results can just read your precise description, implement it, just pick up your best hyperparameter configuration, run the experiment, get the results, exact results. Okay, so now that is how good your reporting of the model should be. Okay, now then I want to talk about another important thing, which is the concept of training loss and evaluation metric. Okay, often we are not directly optimizing our evaluation metric. Okay, in those cases we have to be extremely careful. So to give you an example, let's say you want to do some classification task. Now the evaluation metric is accuracy, right? Like it's like a 0 or 1 function, right? Like so 0, 1 loss is what we want to minimize. But as we have seen in this course, 0 1 loss is very difficult to minimize. So we would often go with surrogate losses, right? Like so, can people tell me what are all the different surrogate losses for 0 1 loss? Well, this lecture I think is also useful for your revision for the exam. So what are all the different surrogate losses that we have seen for 0 1 loss? No answers? Hinge law, okay, yeah, NLL, which is the log likelihood. We have seen hinge laws. What else? This is also called as cross entropy. What other losses we have seen so far? Exponential loss, okay. MSC, right? We have seen all these losses. Okay, now when you're using surrogate losses, you have to be careful, okay? So if your training loss is going down, but your validation performance is very low, then there is some mismatch between the training loss and the evaluation metric, okay? So you have to be careful to see that when the training loss goes down, your validation performance should go up. Fine. So like if your training loss keeps going down, so this is my, okay, maybe I'll draw better. So when my training loss keep going down, but my validation performance, okay, see that I'm using training loss and I'm comparing it with validation performance, which is often accuracy or something else, like it should go up as the training loss goes down. If it is not going up as training loss goes down, then there is a mismatch between your loss and the evaluation metric, and you need to be careful about it. Okay, so this is something that you could easily monitor and figure out. Okay, then the next useful tip. So this is something that I like very much. And probably this is probably like a very useful tip that you often don't see in like the normal lectures, which is basically you should first overfit your model. Okay. Okay, just give me 1 second. Overfit and then regularize. Okay. So here's the thing. If you start with a small model, you cannot be sure whether you have enough capacity to learn this task. Okay. So now the trick here is to start with a high capacity model where you're sure that there is no underfitting problem. Okay. And then add regularizer to reduce the overfitting. Okay. So now often you have these two regimes, right? Like, so this is the model capacity. Okay. Now, as the capacity of the model increases, you start overfitting, right? Like initially you will be underfitting. Initially you will be underfitting. Always, what curve should we look for? Let's look for the training loss. Okay, so, or validation loss. Okay, now this is how the curve would look like approximately, right? Like, so your validation loss is increasing, and after some point, it starts shooting up. Like, so this region is overfitting, and this region is underfitting, right? And there is a sweet spot, right? Now, in reality, it is very difficult to find the sweet spot. Like, it is very difficult to know what exactly should the capacity of your model be. So, for example, if you pick a model here, okay, now you pick this capacity, you train as much as you want, you can never reach a good performance, final performance, simply because this model does not have enough capacity. Okay. However, if you choose a model in this side and start regularizing the model, then you could actually make it have achieved the best performance. Okay. So now the trick here is to first overfit the training data, then you regularize. So you would regularize by adding L1 regularization or L2 regularization or batch norm or like dropout. So any other fancy regularization technique that you could think of. Okay. Okay. So any questions so far? No questions? Everything is clear? Okay, so I would probably have like one final tip. Well, I did not plan it to be 10, like now it's 10. So you have to be careful while using the test set. Okay, so you would often report, like when you're reporting, like when you're printing things in your like experiments, you would often print the training, validation, and test performance at every epoch, okay, in every epoch. Okay, now when you're printing the test performance every epoch, it is often only as a convenient thing to do, in the sense like you would print the test performance in every epoch, but you will not see it. You will see only the validation number to choose the best model. Okay, now it is very, very, very important that you don't use your test, like you don't see your test performance. Okay, so it's better if you just don't compute your test performance throughout the training process. So you should always just do training and validation performance. Now you could tune your model using the validation set, like do extensive hyperparameter tuning, do model changing and everything that you want. Now finally you have the best hyperparameter, right? Like, so now you take the best configuration for hyperparameters and run the test set performance just once. Okay, now this is very important. There are even researchers who have worked for like 10 to 20 years in machine learning publishing papers in conferences where they accidentally tune their model on test set instead of validation set. And there are also famous papers where authors retract the paper because they just found out after publishing that the code was buggy and it was using test data instead of validation data for tuning. Okay, now this is the most common mistake that even experts in machine learning can do. So I would highly encourage you to be careful and like just check every time that you are not leaking test performance to their model. Okay, now there is also another philosophical question here, which is, when should I first see my test performance, right? Like, so for example, like if I am working on a project where like I have to design a solution to deploy, okay, now I would come up with a decent solution based on the validation set. Then I would compute the performance in the test set. Let's say I'm not happy with the performance. Like my performance in test set is 65 percentage. Can I go deploy this machine like algorithm? No, probably not. So I want to go back, revisit my modeling side. Like I repeat the modeling part, like do more experiments and come up with version 2 of the model. Now you go back and test with the test data. The performance is 80, it's not good enough. You go back, do all the process and come again, like your performance in test data is let's say 96. Now you think it is good enough, you deploy the system. Okay, now this is a bit of a gray area simply because we are seeing the test performance more than once in between the projects, right? But in this case, it's kind of unavoidable. But essentially, what is happening here is your test performance, like your test set is kind of leaked to your model, not through the training process, but through your eyes. You see these test performance in the end, and sometimes like you use this information to do more like work on the modeling side, right? Like so now this, whether this is right or wrong is a different question, but this is kind of unavoidable if you care more about the final performance in more practical settings. Okay, so I think I would stop here. I still had few more tips written down, but I think we would stop here. If there are any questions, I could take a few questions. So is batch norm a technique for reducing overfitting? Well, technique. Well, there are many interpretations for batch norm. Like the interpretation that we have seen in this course is it's helping in vanishing gradients, avoiding vanishing gradient. But there is also, well, no, it is correct. So there are many interpretations, but it has also been found to be a good regularizer. Um, okay, so we will have the PDF for the next lecture. For this lecture, I really did not have time to prepare the notes. I I don't I think for the last 4 or 5 days, like you're just not sleeping. So I totally did not have time to write down. Probably I could write down these um, after the next lecture. So yeah, well, A3 grades are done. It is just I am stopping. I was the blocking point because I was not available for the last few days. We will release it soon. Sorry for the delay. Okay, so I will stop the recording if the questions are more about logistics.